So I have shared my slide. It is visible to everyone.
Yes, sir.
Yes, sir.
Okay, thank you. Uh,
Yes, sir.
thank you. So last class we are discussing on the compiler, and we actually we looked at certain how the architect helps the compiler and how the compiler helps the architect. And I've left only the two slides are left. You can read the two slides, and if you are not able to follow, then we'll discuss. We have spent enough time on that on the basic introduction. So let us skip that basic introduction now, and let's look the another topic called the pipelining, and we'll discuss in great details of the pipelining because the all the present day the computers are based on the pipelining architecture. Let's discuss what is a pipelining. A pipeline is a implementation technique whereby the instructions are overlapped in execution. So instructions pass to different stages of the execution, and in a pipeline we overlap the different stages. Now if you want to overlap the instructions in a pipeline, then those instructions must satisfy certain properties such that the instruction can be overlapped. The pipeline takes advantage of the parallelism that exists among the actions needed to execute an instruction. Look at to execute an instruction, we know that certain operation need to be done. You need to fetch the instruction from the memory, then you need to decode the instruction to find out what operation to be done. Then you need to read the register or read the memory location to get the operand. If the operand, once the operand are available, then you have to perform the operations. Then the result may be written back into the memory location, or it may be written back into the some register. So a number of operations need to be performed to execute a given instructions, and pipeline exploit what parallelism that exists among the different actions to execute an instruction. Look at what parallelism, that if a instruction is executing in a execution phase, that means that instruction cannot remain in another stage of the execution. Either it will be in execution stage or it's in the decode stage, but the same instructions cannot remain in two different stage at the same time. You cannot have an instruction in the execution stage and the same instruction in the decode stage at the same time. Each step in a pipeline completes a part of an instruction. So the pipeline has a different stages or called a different steps, and each steps perform a certain part of the instruction. So if the typically we'll discuss that a instruction will fetch the different steps that the instruction pass through to execute. For an execution is the fetch the instruction, decode it, execute the instructions, then write in the memory or write back to the register. So these are basically the 5 stages that we'll discuss. So each steps in a pipeline perform a certain part of the instruction. The different steps are completing a different part of the instruction in parallel. This is what he says, that it takes advantage of the parallelism. And I said that no two instructions can be at two different sorry, no instruction can be at two different stage at the same instant of the time. So the different steps are completing different part of the instructions in parallel. So if one instruction in the execution stage, the other instruction may be in the decode stage, another instruction may be in the fetch stage, and some other instruction may be in the write back stage. So different instructions are in the different part, different stages of the executions, and they'll be executing the parallelly. Each step is called a pipe stage or a pipe segment, and the when it executes in a pipeline, the instruction has to move from one stage to the next stage at every clock cycle until the instruction completes the execution. So the time required between moving an instruction one step down the pipeline is a processor cycle, or basically we will call it the clock cycle also. So in every clock cycle, the instruction is to move one step down the pipeline. So if the instruction is in a decode stage at a clock cycle t, then in the clock cycle t plus 1, that is in the next clock cycle, it has to go to the next stage of the pipeline. And if the next stage of the pipeline is the execution stage, it has to go to the execution state. And if the next stage of the pipeline is a write back stage, then it has to move into the write back stage. What will be the processor cycle? Processor cycle, how much time it will require to move a instruction down. Now in this cycle, the processor has to complete the certain actions that need to be performed in that particular cycle. Then at the end of the cycle, it has to be moved down the pipeline. Then the length of a processor cycle is determined by the time required for the slowest pipeline stage. Look at, we had different stages in the pipeline, and all the stages may not take a equal amount of time. So the process that all stages is not going to take an equal amount of time, but within a processor cycle, all instruction has to move down the one stage in the pipeline. So the processor cycle should be such that within that cycle, the slowest stage of the pipeline can complete the operation. So the processor cycle is determined by the time required for the slowest pipeline stage. And the goal of a pipeline designer is to balance the length of the pipeline stages. Now, if the length of the pipeline stages are perfectly balanced, let's look at it, the different stages, and all stages takes a different amount of time, and the processor the processor cycle is equal to the time required for the slowest stage in the pipeline. Now if the stages are perfectly balanced, that all stages takes the equal amount of time, then the time per instruction in a pipeline processor is equal to the time per instruction on a on pipeline machine divided by the number of the pipeline stages. So if the stages are perfectly balanced, and the stages are usually not perfectly balanced. Now if for perfect if for the processing the in a pipeline, if you're executing the instruction in a pipeline, the pipeline yields a reduction in the average execution time per instruction. The average time to execute a given instruction is reduced in a pipeline. Now when we are trying to reduce the average time of to execute an instruction, this reduction can be viewed as a decrease in the number of the clock cycle per instructions. You can view it as a decrease in the clock cycle time, or a both. So what you can see in a pipeline, uh, uh, the pipeline may be decreasing the number of clock cycle per instruction, or it can be decreasing the clock cycle time, or the pipeline may be decreasing the both. Now if you have a pipeline, let's say if you had a processor, and the processor takes multiple number of clock cycles to execute an instruction. Let's say the processor take 20 clock cycles to execute instruction, and you pipeline that processor. Let's say it's an on pipeline processor is taking 20 clock cycle, and you pipeline that processor, and now the processor takes a 5 clock cycle per instruction. Now that means you are decreasing the number of clock cycle per instruction. So your baseline is the number of clock cycle the processor the on pipeline processor was taking. This whether you decrease the number of clock cycle per instruction, then you decrease the clock cycle time. Suppose you had a processor that takes a very long clock cycle per instruction. It's a long, it takes one long clock cycle per instruction. Then you can decrease the clock cycle time. Then by pipelining, you can decrease the clock cycle time. So you're reducing the clock cycle time now. Either you reducing the number of clock cycle, number of the clock cycle, or you reduce the number of, or can decrease the number, decrease the clock cycle time, or the pipeline can decrease both the clock cycle as well as the clock cycle, the number of clock cycle as well as the clock cycle, the time. Now, in our entire discussion, we'll discuss about a 5-stage pipeline. That means the pipeline will execute any instruction in a 5-stage. And if you look at the pipeline, you had an instruction set and it implement a instruction set. So we'll consider a RISC instruction set, and let's look at certain properties of the RISC instruction set that helps in the pipelining, or it simplifies the implementation of the pipeline. Let's look at the reduced instruction set, and the reduced instruction set computer is a load and store architecture, and we'll use the instructions, the RISC architecture, or the instruction in the RISC architecture to explain the entire the pipeline, the pipeline mechanism. Now let's look at some of the key properties of the RISC architecture. The certain key properties of the RISC architecture are all operations on data apply to data in the registers. Look at, it's a load and store architecture. Now it's a load and store architecture where the all operations is all arithmetic operations that it's to perform, the operand must be there in the register. So all operations on data apply to data in the register. So if you are performing any data, then the data must be there on the register. Whether you perform addition operation, subtraction operation, multiply, any operation that you perform, the data must be there in the register, and it operates on the entire register, entire number of bits in the register. The load and store operations affects the memory. So it's a load and store architecture. So there are only two instructions that refers to the memory. It's a load and store operation, load and store instructions, and a load and store instructions are the two instructions that affects the memory. And either you read from the memory or you write into the memory. And a load instructions, it moves the data from the memory to the register. So load it from the memory to the register, and a store operations, it moves the data from the register to the memory. Store, it write, so it's a read and write operation on the memory. A load is a read operation on the memory, and it reads from the memory and write to a register. And a store operation is a write operations. It's write into the memory from the register. And the load and store operations operates on the full register, whether the registers are 16 bit or a 32 bit, the entire register is read or the written. The next properties of it RISC is the few instruction format. The number of instruction format that's available with all instruction typically being one size. So it said, if you look at, we discuss about the variable instruction format and fixed instruction format, two extremes, and a hybrid of these two, where you had a few instruction format, but all these are of fixed size. So here the RISC architecture has a few instruction format. Basically, it is a 3 instruction format with all instruction typically being one size, a fixed size. If you look at these are 3 key properties, and these 3 properties simplify the implementation of the pipeline. So let's look at the effect of these three properties, that all if the operation is to perform on the data, then the data must be available on the register. Two instruction only refer to the memory, and all instructions are of fixed size and only have a very few instruction format. These three property simplifies the implementations of the pipelining, and that is why the these instructions were because these simplifies the implementation of the pipeline, so the instructions are designed in this particular way. Now we'll discuss a risk architecture, and Mips is our the Mips is the default architecture is the risk, and we'll be using the Mips architecture which is based on the risk. So most risk architecture have three classes of instructions. It's a ALU instructions. Now, moment we say is a ALU instructions, the instruction perform operations on the operands which are available on the registers. So if the ALU instructions, the ALU instructions needs a two operand, and both the operand must be available either in the register, or one of the operand is available in the register and the other operand is the immediate field which is available in the instruction itself, and this immediate field is sign extended, and we call such type of instruction as ALU immediate instruction. So it's sign extend, so it's a both operand are in the register, or one operand in the register and other operand is a specified in the offset, and you sign extend the offset and perform the operation. So some of these operations you can call it a add. It's a, let's say it's the add instruction. Now we'll use certain uh, terminology, certain these Mips instruction set, and in a Mips instruction we'll be using the 64-bit instructions. It's called the Mips 64. So it's all 64-bit instructions, and if this is add instructions, if it is written add, it's a 32-bit add, and if you write anywhere you'll find the word D, find the alphabet D. So it is a 64-bit operation. So it says it is a 64-bit add, and if you write L D, there is a D either in the mnemonics. If you find a D either in the prefix or in the suffix, so it's called a 64-bit. So it is a 64-bit load. Then if you find something called I in the instructions, say if I'll write add I, so this indicates immediate. So it says this a ALU immediate instructions, and if you write D, this becomes a 64-bit instruction, and wherever there is another alphabet called U, it's called unsigned operation. So if I'll write here U, this is a unsigned operation. Now this I for immediate, D either in the prefix or the suffix of the mnemonics, it is 64-bit and used for the unsigned. So I can write D, sorry, somewhere. So I can write D add unsigned. So it is a 64-bit unsigned operation, and if you write D subtract U, again it's a 64-bit unsigned operation. The next class of instruction is a load and store instruction. Now if it is a load and store instruction, in the previous slide we discussed that this the risk architectures, it's a load and store architectures, and they refer to the memory using only two instructions, either to read and write. The load is to read and the store is to the write. Now when you perform the memory operations, then you need to know the address of the memory location. If I am to read the memory, then I need to know the address of the memory, and if I am to store it, then I have to know the address of the memory location where a register has to be stored. So if I want to read it, the address is to be known, read it from the memory, and the destination register has to be known. And if you want to store it, the source register has to be known and the destination memory location has to be known. So now you need to compute the address of the memory location. So in the load and store instruction, you need to compute the address of the memory location, and we call those the effective address. Now these instructions, the load and store instructions, it take a register source, so called the base register. So here in this load and store instructions, there is something called a base register. There is something called a base register. So a base register is specified, and there is also an immediate field is specified, and this is a 16 bit in the Mips, and this is, we call this immediate field which called the offset field. So what is provided? The base register is there, the offset is there. So now you need to compute the address of the memory location. To compute the address of the memory location, you sign extend the offset. The offset is signed. Look at these registers are of 64 bits, so you sign extend the offset and you add the content of the base register along with the offset. So this is a ALU immediate. This is a the add the offset, and the result of the base register plus the offset, you give the address of the memory location. Address of the memory location, then you come fetch the address of the memory location and store it in the register which is again specified in the instruction. So yeah, here the destination register is specified, a base register is specified, and offset is specified. So you add sign extend the offset, add to the content of the base register, then that will give the effective address of the memory location. You fetch from that memory location and store it in another register which is specified in the instruction. And if it is the store, then the source register is known, so effective address is computed to store the content of the register which is specified in the instruction on the memory location which effective address is computed. Now if you are using the instructions, let's say load, it's a 64 bit, it's a load one, it's a 64 bit, and if you are using SD, it's LD or SD, it's a load, it's a 64 bit, and store is a 64 bit. So here the register is a 64 bit is written into the register, and here a 64 bit is written from the memory from the register into the memory location. Then the third class of instructions, or the branch and jump instructions. Now branches are conditional transfer of the control. Look at in a branch or a jump instructions, the control is transferred from one location to the another location. And branch, it's a conditional transfer, so you test certain condition, and depending on the result of the condition, the control is transferred from one location to either the control will be transferred or the control will not be transferred depending upon the outcome of the branch. Now the two ways of specifying the branch. So look at in one of the slides in the previous lecture, we have specified the different ways the branch condition are specified. Some can check the condition code, some checking the certain registers, and some of this some of the architectures, they test certain the flags. So there are different ways the architecture tests their conditions. So here there are two ways. This risk architecture, there are two ways of specifying the branch condition in a risk architecture. One is with a set of condition bits, and this also is called the condition codes. So So you perform a certain operations. Then on the as a result of these operations, certain bits or the flags are it's set, and depending upon the condition of the bit set or the bit reset, so jump the branching is being decided. The another way is to compare between a pair of resistor or between a resistor and a zero. Now, so if there are two ways it can be done, whether by looking at the condition codes and by comparing between a pair of resistor or between a resistor and zero, and the MIP architecture that will be, or the MIP instruction set that will be using, uses the second one, the comparison between a pair of resistor or between a resistor and a zero. So we'll use between either between a pair of resistor or between a resistor and a zero. So this is what this is how the MIP instruction set is going to check for the branch condition. Now, if a branch is to take place, let's look at what does the PC contain. The PC contains the address of the next instruction. Now, if it is a branch instructions and the branch is going to take place, that means the control is to transfer to a instruction which is not equal to the next instruction after the branch instruction. Then you need to obtain the address of the target, and the address of the target is obtained by adding the sign extended offset to the current PC. So the PC plus offset, you add the PC plus offset, and once you add the PC plus offset, you get the address of the target. That target must be again written back into the PC, and you start fetching the instruction from the target. So these are the RISC architecture classify the instructions into three classes, or there the instructions are ALU instructions, whether it's a load and store instructions, is a branch or a jump instruction, and jump instruction are unconditional jump, and we'll not be discussing about the jump instructions. We'll discuss only the branch instructions. Now we consider only comparison of so in this MIPS architecture, that will be MIPS instruction set that will be considering in our discussion. We'll consider only the comparison for equality between two resistor to determine whether branch is going to take place or branch is not going to. So here we'll compare between two resistor, and if the resistors are equal, a sort of action to be done, and if the resistors are not equal, and another action to be done. In all these architectures, the branch is obtained by adding a sign extended offset to the PC. This is what I have already said, that the current PC is added off with the offset field, which is sign extended offset field, and you get the address of the target instruction. Now let's look at a typical RISC instruction set. This is a 32-bit fixed format instructions, and there are three instruction format, and all the three instruction formats are of 32 bits. The memory access only via the load and store instructions. There are 32-bit. There are 32 64-bit general purpose register, and the register always contains 0. So if in certain branch condition, you can compare a register with register R0. So register R0 always contains a 0. So you can compare that one. So branch equal to, branch not equal to, you perform some operation and you have to compare whether the result of the operation is 0 or not. So you compare with the register R0. So there are 32 64-bit general purpose register, and there are also 32 64-bit floating point register. The instructions have three address. The register arithmetic instructions have a three address. So it's a two source and one destination, and all the registers are in the same place. Look at, there is certain advantage of having all the register in the same place, and that is why the pipelining of these instructions are easier. Now, single address mode for a load and store. Now, look at in a load and store, you need to compute the effective address. And in one of the lecture we discussed that a instruction having multiple addressing mode, multiple instructions, multiple addressing mode vis-a-vis instruction having single addressing mode. So here the single address mode for the load and store, and it uses the base plus displacement. That what I discussed, how to compute the address of the target. The base register is specified, then the displacement, the offset is known. So you signed extend the offset, add it to the base register, that gives the address of the target. A no indirection operation used. Now when you say is a no, indirection operations, you get the address of a memory location by looking at the content of some other memory location or some of the register. What he says in the indirection, that suppose this is the register, suppose you register R, and this register R uh, will give the specify the address of the memory location. So you go to the register R, from the register R you go to some memory location, that will give the address. So this is what we call the indirection. So no indirection is being used here. So the address is obtained by base plus the displacement. Then it's a the branch conditions are simple. So how we test it? The then it's a simple branch condition, and we say that it uses the compare between two register for testing for the branches, and it uses a delayed branch technique, and we'll discuss what is a delayed branch technique in subsequently in subsequent lectures. And certain the variables, the representative of the risk architecture are Mips, IBM Power PC, DEC Alpha. These are all the representative of the risk architecture, and we'll discuss the Mips instruction set. And it is a we'll discuss on the 64-bit Mips instruction set. This is the the instruction format. Now, if you look at the instruction format, all are of 32 bits. Now, if you look at in all cases, the operations are at fixed location. Now, if you look at the register operations, the source and destination registers, look at there are 3 registers. All 3 registers are at a fixed location. If you look at register immediate instruction, the register immediate has a registers are at a fixed location. Branch, the registers, they are at a fixed location. And if it is a jump, if it is jump instructions, then this there are the target, there are 26 big target instructions. So all these instructions are fixed, and the register are at a very fixed location, and there is advantage we'll discuss in the subsequent slide. What is the advantage of having the register at a fixed location vis-a-vis the register at any location. Now, before we go for the implementations, let's discuss how the instructions are executed in a processor without pipelining. Now, if we know that how the instructions are executed without a pipelining, then we can design a pipeline, because the instruction execution, whether in a pipeline or in a on pipeline machine, is not going to change. The instruction will execute exactly in the same way. So let's discuss how the instruction, how the risk instructions is executed without without pipelining. And we'll here we'll take the instructions, we'll take a 5 clock cycle. So here all instructions will going to take a 5 clock cycle. So in every clock cycle, some operations to be done. So there should be a 5 different operations that need to be done to complete the execution of the instruction. Let's look at the what operations are done in the 5 clock cycle. and in every clock cycle some operation has to be done. So the first is the instruction phase. So let's look at what are the operations are going to do in the instruction phase. So in a instruction phase, you fetch the instruction from the memory, and any instruction that you fetch from the memory is stored in the instruction register. So where the address is stored, the address is stored in the address of the memory location from where the instruction is to be fetched is there in the program counter. So you access the memory location whose address is available in the program counter and store it in the instruction register. So the instruction register contain the instruction that need to be executed, and the content of the instruction register uh, should not get changed until the instruction is complete in the execution. Then the program counter is incremented by 4. This is 4 because the instructions are 4 bytes. So I am incrementing the program counter by 4. So program counter is incremented by 4 and it is stored in a temporary register called next program counter. So what does NPC contain? The NPC contain the address of the next instruction to be fetched from the memory. This is what is done in the instruction fetch cycle. The next is a instruction decode or the register fetch cycle. So you fetch an instruction, then after fetching the instruction, you decode the register and you decode the instruction and you fetch the register. Now let's so you decode the instruction that is being fetched in the instruction fetch cycle and read the register corresponding to the register source specifier. Now uh, we do not know what is the operation to be performed at this stage. This stage, two operations are being done. You are decoding the operation to be performed and you are also reading the register. Now if you look at the instruction format, the registers are at a very specific location in the instruction format. So you know where are the source register. You do not know whether it's a ALU ALU instruction, or it is a register immediate ALU instructions, or it is a branch instruction. We do not know, or it is a load and store instruction. We do not know what the type of the instruction, but we know that where are if it is a if it is a register ALU instruction, or then we know where are the source operand. The location of the operands are fixed because the location of the operands, the register specifier are fixed, or the register operands are fixed. Then you can access the register. Now you access a register, then you may not require. Suppose it is a branch instruction, but you access the two source two register. And in a branch instruction, then you don't need two registers. So you can discard the whatever the register value that you have read, because the read is a non-destructive process. So you can read it, and if required, you can use the value. And if you don't require the value, you can discard it. So you are not going to pay a penalty. But if you do not read at this stage and you try to read at a later stage, then you pay a penalty. That means you will need one more clock cycle to read the register. And here the instruction decode stage, two operations are done, decode and they read the register corresponding to the source register specifier. Then do the equality test on the register as they are read for a possible branch. Now let's look at, we also do not know whether it is a branch instruction or not, but we know that the for performing a branch operations, so it performs an equality test on the register. So here also the registers are being already being read, so you perform a equality test on the register. So perform a equality test on the register as they are read for a possible branch. We do not know whether it is a branch instruction itself, but you are comparing between two register for a possible branch instruction. Then sign extend the offset field. Now The offset field are it also at a very fixed location. So you extract the offset field from the location, but we do not know whether it's a ALU instruction or it's a ALU immediate instruction or it is a branch instruction. But the in all this the offset field says a specific location. So you extract the offset field and you sign extend the offset field. It may require the offset field may require, the offset field may not require. If it is a branch instruction, possibly you may need the offset field. If it is a ALU immediate instruction, then you need an offset field. We do not know what type of instruction, but you do all these operations because all these operations are a non-destructive operations. Then compute the possible branch target. Now we do not know at this stage it's a branch instruction or not, but if sign extend the offset field, you know the PC, then if you have a adder here, if you had a adder in this stage, then you add the offset and the PC to get the possible target address. So a lot of operations are done in the instruction decode stage. Decoding, let's answer this question. Probably I have already answered to this one. The decoding is done in parallel with register reading the register. Now the decoding is done in parallel in the register reading the register because reading is a non-destructive process. So you can read the register, and if the register is not required, whatever the register you have read, the source register you have read is not required, it can be you can discard the source register. But here if in the architecture or in a system where it is sensitive to the power, then reading cannot be done, reading should not be done, because when you reading, then we are consuming some amount of power in for reading the operation.
Hello, sir.
Yes.
Sir, you said we will be discussing architecture of 64-bit, no, sir?
Yes, this will discuss 64. We have will consider only the 64-bit instruction set, MIPS 64.
Sir, then next program counter is PC plus 8, no, sir?
This is I am looking. Yes, what you correct, what you say, your observation is correct. I am just explaining on the RISC instruction set where the instructions are of 32-bit format.
Okay, okay.
The MIPS will be discussing of 64 bits. MIPS 64. If I use a instruction LD, then I am referring to a 64-bit instruction. This I am basically explaining on a architecture with on pipeline, how the instructions are executed and on pipeline machine on a RISC with a 32-bit instruction.
Okay, okay.
So next is we have decoded the instructions, we have faced the instruction, we have decoded the instructions. Then next is the execution and effective address. Now let's look at if it is a register instruction or a register immediate instructions, then you need an ALU. You do perform operations. You add two operand if the operands are available in the register. If it is a ALU immediate instructions, one of the operand is available in the one of the operand is available in the register, the other operand is the sign extended offset, you perform the ALU operation. Now if it is a load and store, then you have to compute the effective address in this cycle. So the ALU operates on the operand and performs one of the three functions. It is a memory reference instruction. Now we have fetch, we have decoded, and the instruction is a memory reference instruction. If it is a memory reference instruction, then the ALU adds the base register and the offset to address. So look at if it a memory reference, if it is load and store, which refer to the memory, then you need to compute the effective address, and computing the effective address, you add the base register plus the sign extended offset, and that operation is done in the execution stage. If it is a register ALU instruction, now if it is a register ALU instructions, the ALU perform the operations specified by the ALU opcode. on the values read from the register file. So if it is the sorry, if it is the register ALU instruction, that means both the registers are read in the instruction decode stage, and the ALU is performing the operations is specified by the ALU opcode. So if you're it can be addition, or it can be a subtraction, or some operation which needs two operand that is read in the two operand read in the instruction decode stage. Then next is it can be a register immediate ALU instruction. If it is a register immediate ALU instructions, ALU performs the operation specified by the ALU opcode on the first value read from the register file and signed extend the immediate. So if it is a register immediate, one of the operand is read available in the register. The other operand is the offset, which is sign extended in the instruct decode set, and the ALU performs the addition operation of this register and the sign extended offset. So in this stage, if you look at in the execution stage, two different operations are done. One is you are computing the memory address, and you are also performing some arithmetic operations. Then why two different operations are performed in the same clock cycle? Can anyone answer to this question? We are performing in one clock cycle, two different operations are performed. Look at in the previous stage, many different operations are performed in the instruction decode stage. You read the registers, you sign extend, you compare with the branch for a possible target, then you compute the target address, because all of them can be done, because none of them are all operations are non-destructive, so you can perform this operation. Now in this in the execution cell, two different operations in the execution of an instruction are put it in one cycle. In the same way, why two different operations are put in the same clock cycle? Can anyone answer to this question?
Sir,
Yes.
sir, I think the memory read and register read involves the local bus, the main bus. That's why.
No, it is not, it's nothing to do with the bus. Is look at the operation only. Don't look at the bus. Don't go back to the much hardware level. Look at the more abstract level, at the operation level. Okay, so let's look at, let's take any instruction, right? You take any instructions. In that instructions, the either you perform a execution. What are the different type of instructions we have? We have a memory reference instruction, we had a register instruction, or you have a register immediate instruction. So these are the, or a jump instruction, right? These are the different type of instructions that you required. Now in any of these instructions, either you compute the operation or you compute the effective address. Look at in the branch instruction, we are already computing the target in the instruction decode state, because we have put another ALU in the instruction decode stage. So you are not using the main ALU in the data path. Now if you look at register ALU instruction and register immediate, here these instruction needs an ALU to perform an ALU operation. So it does not compute if it is a register ALU operation, register immediate ALU operation. So it is not, this instruction is not computing the effective address. Where the effective address is required, the effective address is required only in the instructions which refer to the memory, the load and store instructions. So if the load and store instruction is computing the effective address, so it is not performing any any execution. It's not performing any the arithmetic operation. So either a instruction perform an arithmetic operations, or the instruction compute the effective address. So two operations are never done in any instructions, as a result of which two different operations are done in the same clock cycle. These two operations are mutually exclusive. If you look at from the instruction point of view, a instruction is not going to perform two operations at any point of time. it's computing also address and it's computing the effective address. It performs the execution. So both are mutually exclusive. Because they are mutually exclusive, they are put in the same clock cycle. So this is the question that I asked. So let's look at. Next is the memory access. So you have fetch, we have decode, we have execute. Then it's a memory. Why you need a memory? Suppose it is a load instruction. In case of a load instructions, the what do you do it in the execution stage? You have compute the effective address. If it is a store instructions, what we did in the execution stage, we have computed the effective address. So if it is a memory reference instruction, then in the execution stage, we have computed the effective address of the memory location to be read or to be the written. So if it is a load instruction, the memory does a read using the effective address, and the effective address is already we computed in the previous clock cycle. And if it is stored, then the memory writes the data from the register using the effective address. So effective address is computed in the previous cycle, and the register already being read in the instruction decode stage. So thus we do in a memory access. Now if you look at, I had a add instruction. Now this add instruction is not going to perform any operation in the memory cycle stage, because the addition it perform operations on the register that is already read in the instruction decode stage, and it has to write back into the register file. Now write back cycle, the last stage, the write back cycle. So it is a if it is a register ALU instruction. Now whatever the operation, now if it is a arithmetic operations, the result of the arithmetic operation has to be written back into the register. And if it is a load instruction, you have read it from the memory location in the previous cycle, in the memory cycle, and this need to be stored back. It needs to be stored in a register. So if it is the register ALU instructions, then the output of the ALU. So this is the output of the ALU. The output of the ALU will be stored at a specific location in the register. So this is my destination register, and destination register are fixed. Source is fixed, destination is fixed. And if it is the register immediate, the register output is again stored in the register, which the destination is also fixed. And it is the load instruction. Look at, in a load instruction, you have read it from the memory. You have read it from the memory, and you'll be writing into the register, and the register location where it is to be written is also fixed. So this is ALU output and load. These are temporary register. So output, you perform arithmetic operations, it is written into a some temporary register called ALU output, and is written to this the corresponding register. And if the load instruction, it is read from the memory and stored in a temporary register called the LMD. This is load memory data, and at the end of the clock cycle, you can write in the into this the register. Now this already 55, so you can leave the team so that you can join in the next class. But we'll analyze the how much clock cycle it takes for executing the branch instruction, and this analysis is more important. So you can leave and join you can leave the team and join the next class.
Hello, sir.